every week, but some Wednesday every week. I mean, don't say that in front of me. I get offended. I mean, again, still. So let's not talk about it. So one thing is that, do you guys have like 5 minutes that you can be late, or you have to be on time? 5 minutes? Yeah, I see. So what can we do to make it better for you? I tried to move next to that. There is no other large enough room next to that at this time available. That's the problem. I really, really tried, I promise, but it didn't work. So what can we do? Should I just send you a short video of the time you missed? And can I have the days that you have quiz on Wednesday, can I have you sit like on the aisle? And then you guys leave and I send you just that piece that you missed. So I send that, I put it in the announcement on Wednesdays. Fair game? So you leave 5 minutes early. Okay, so this is not gonna happen again. If you guys sit on the aisle and we now know on Wednesdays I'm supposed to do that. But we did go through that iClicker, and they said it's going to be extra credit for us. So I'm giving it again. So let's start section. Got that. I said I'm going to throw that away, and I didn't. Section 14.8. It's called Lagrange Multipliers. So what is up with Lagrange multipliers? I'm going to explain it very briefly. In 14.7, we did closed and bounded method at the end. Now, when I say closed and bounded, means boundary are included. 14.8, and you remember, boundary included required what? Parametrization. It was kind of a mess. Also, parameterization not always possible. 14.8 give you a method for boundary. Boundary only, not the entire thing. And what it does is that it gets rid of the parameterization entirely. So you just use that method to do stuff, basically. Boundary, if there are multiple pieces, if it's piecewise defined, hint, hint, there are corners. When there are pieces, hint, hint, corners, corners. Pieces or corners. This is difficult. This is a lot. So sometimes if there are pieces and corners, you still want to use the previous method. This is more boundary that is smooth. So boundary like this is good, check mark. This one, go 14.7 is easier. Fair game? 14.8, 14.7. That's the differences. Now, what it does, and I define this, two curves are tangent at P, meaning that P is included in both curves, if the tangent line is the same. Tangent line at P is unique, is the same for both. Now, the method of Lagrange multipliers actually uses the fact that if you have local extrema on the, what is it called, boundary, if you have a local extrema of the function, boundary is also called what? Can anybody tell me another name for boundary? Constraint. So boundary curve or constraint function. So if there is a local extrema on boundary, then the level curves of the objective is tangent to the level curve of boundary. Curve of the boundary at that point. So that's what it does. Let me write it down because I'm repeating this. So in Lagrange multiplier method, when objective is f of x, objective function, f of x and y, that's the one that you're optimizing. And the constraint is g of x and y equal to k. Level curves at, if A and B gives extrema on g of x and y equal to k, then level curve of f at A and B is tangent to g, x, and y equal to k. It's a lot wordy. Let's do it by picture. You guys are ready? Half of you guys have seen this. More than half. Do it again, do it again. What? Okay, let's see what's happening. That function is the last function we optimized in 14.7. That was the constraint. The last example in 14.7, that was the constraint. Can you guys tell me where is the constraint right now in this picture? Just a black circle, right? So the black circle is the curve of the constraint. What are the other curves? Level curves of f, the objective function, right? So can you guys tell when the level curves goes through that, you're expecting level curve a little bigger, a little smaller, also goes through it. So it cannot be an optimal. It cannot be optimization when the curve goes through it. But when the curve is tangent, can you see that's tangent? Where is it? That one is tangent, and that one is tangent, and that one is tangent. When they're tangent, you're expecting that the level curves with higher value and lower value are not, either higher value or lower value are not going through it. When it goes through it, you're expecting both sides go through it. Because it makes a little level curve over here or over there, right? So you guys know the answer from example 2. What is the answer? And that's you can see the level curve right there of the function. So that's the method. Can I stop? That doesn't sound right. 4, 3, 2, 1. I've never had this few people in the class. Friday, but I mean, still, 0. Text your friends if you can to come in. They're missing a lot. So the entire thing, that was the iClicker. On your lecture notes, you have this. This actually is not a bad idea just to look at, because when you're looking at this level curve, what I was trying to tell you is this. If this is the curve over here, the cyan curve, is the constraint. And you can tell that if I just look at the places that the cyan curve is going through level curves, not the place that is tangent, you can tell that, oh, I can get a little bit more level curve at 6.5, and I can get 7 and stuff right next to it. And then I can also get 5.8 over here. And so when it goes through it, this is a point that it goes through it. You can see that level curves that are bigger and smaller are right there. But when it's tangent, then all the stuff up here are missed. That's why the local happens, basically. Local extrema happens. Because one side of it, you don't have any level curves that are higher or lower. And then I'm trying to dumb it down. The proof of it is also doable. Proof of it is on the next page. Huh? So the proof of it is also on the next page, and it talks about, there we go, I'm on the wrong page. These are the handout only material. And the proof is right here. And what it talks about is that, so the statement is this. Assume again, f of x and y and g of x and y are differentiable if f has an extremum on the constraint g of x and y equal to k, then what happens? Constraint on this at points. Let me see. At point A and B, then basically this curve is going to be parallel to level curve of f. What is gradient of f to level curve? Orthogonal. What is gradient of g to g? G is a level curve to constraint curve. This is a level curve of g. Orthogonal again. Two things that are orthogonal to the same thing are parallel. They're parallel. So then the gradient of f at A and B is parallel to gradient of g at A and B. That is gradient of f at A and B, which is a vector, is going to be a constant multiple of the other one. That's the story. So gradient of f is orthogonal to level curve of f. Constraint is level curve of g. Gradient of g is orthogonal to that, so the two of them are parallel. That's all it is to it. Yes, you can prove this, and it requires a chain rule right there. You can take a look, because g of x and y can be parameterized by r of t. And then you say that A and B is equal to R at some t0. Then you parameterize f at R of t. You take the derivative of that. You set it equal to 0. That would be just gradient of f at A and B. dot r prime at t0 equal to 0, and it tells you that gradient of f is orthogonal to the curve of the constraints. Therefore, the two gradients are parallel. That's the proof. Sketch of the proof. And I use chain rule here. But it requires a little thinking. What I did is just to set you up. If you want to read the proof, that's the starter. That's all. I didn't do the proof. Remember, I did a little sketch of the proof, so in case you're interested in reading it. I didn't do the proof. Abraham, do you have a question? I said it right. Abraham. Yeah. Okay. I have an Abraham also in this course. So now, fun, but I didn't tell you how to do this. Have I told you yet? No. So let me tell you how to do this. Method of Lagrange multipliers. So the first thing that you guys do, if f and g, f is the objective, g of x and y equal to k is the constraint. 1, set gradient of f equal to lambda. Everybody have seen lambda before? It looks like x is just missing one piece. Lambda gradient of g. This gives you two equations. Then use the g of x and y equal to k. Third equation. Solve for x, y, and lambda. If you can skip lambda, skip lambda. If you can eliminate lambda, do it. So you don't have to solve, but sometimes you have to solve for lambda to solve for x and y. Then 2, evaluate if at all points in part 1, 3, the largest in part 2 is max, the smallest is the min, under a few conditions. The condition is if g of x and y equal to k is bounded and closed. Right? If it's closed and bounded. I will do an example that is not bounded or closed, but you know by experience that you achieve a local max and min, and that's the only one that you reach. And you do one in your lab. Fair game? So generally, I want it closed and bounded, but if by experience you know one of the extrema exists, this also detects that extrema, even if it's not closed and bounded, if the constraint is not closed and bounded. That's the fun part of it. Okay. Lagrange multiplier is heavy in econ, business, and that's why we cover this, because you guys probably will do this with them. You will see it in machine learning. Everybody uses machine learning to some extent. It will come up. Okay. So next thing, do you guys look at this? Does this look familiar? What was that? That's example 2 from last time. from 14.7, right? The one that I just did the iClicker on. So let's do this through the Lagrange multiplier. What's the first step, my friends? First step? Gradient of which one? F, which is 2x minus 4y, right? Oh, whoa. Then what's the next one? Minus 4x plus 2y. What's next? Gradients of g, x, and y. The two of them are supposed to be parallel. Parallel means this should be a constant multiple, and I'm going to use lambda. Lambda is not the best, but it's what you see everywhere. So I'm going to say gradient of f is equal to lambda gradient of g, right? That means that the first component of that is equal to lambda first component, lambda first component of this, first component of the other one is equal to lambda first component of this. Fair game so far? Yes. Thank you. I mean, in long run, it doesn't matter because they're parallel, but because the 2 was multiplied by both of them. But thank you so much. I forgot the 2. Please put it back in. Now, how many unknowns do you have here? 3. Can I solve for all 3 unknowns uniquely? No. What do I need? A third equation. Where is the third equation? It's given. It's the equation of the constraint. The constraint. So my general idea is to solve for lambda and try to eliminate it. Sometimes it works, sometimes it doesn't. That's why I said you may have to solve. But if you can, they skip. So how do I solve for lambda? So these are the 3 equations. I solve for lambda. How do I solve for lambda here? 2x minus 4y over 2x. How about the second one? Lambda is equal to minus 4x plus 2y divided by 2y. It simplifies a little bit too, right? Factor a 2 out. And these 2 are going to simplify and factor a 2 out. Who can tell me what's the next step? So lambda is out. Whatever I'm writing is x. Don't get confused with lambda. What's the next step, my friends? Lambda equal to that, lambda equal to that. What do I do to eliminate lambda? These 2 equal to each other. So I have x minus 2y over x is equal to minus 2x plus y over y. Right? Right. Now, what's the next step? Multiply by x times y, right? So I get y times x minus 2y is equal to x times minus 2x plus y. That is xy minus 2y squared is equal to minus 2x squared plus xy. What else? And then what is remaining? Y squared equal to x squared. Now, do I have any more equations to use? I'm going to the left. I'm sorry, I'm going from right to the left, not left to right. So I'm going to go like this. Why? Because then I'll pull that in also. Put in y squared as x squared. You get x squared plus x squared equal to 1. That is 2x squared equal to 1. What is that x equal to? Plus minus square root of 1/2. What is that also called? This, right? plus minus square root of 1/2 is also plus minus square root of 2 over 2. So what is y here? Y squared also is equal to 1/2. So y squared also equal to 1/2. So what is y? Now, how many points is this? Was the plus and minus of y and x related? In this case, they weren't. They were independently plus minus. So I get 4 points out of this. Everybody agrees? Yes. Cam? No, Mac.
Why is there not like 2 in front of the y squared there?
Oh, I simplified it. This 2.
Oh, I meant on the other side, sorry. You just did. 2x squared had 1.
Oh, yeah, this means x squared is equal to 1/2, so I skip this step.
I see.
Skip this step. Yeah. You heard what I said. Say it 5 times. So now I have, can I not do this last step? I probably could skip it. So the points I found are square root of 2 over 2, square root of 2 over 2, negative square root of 2 over 2. Do you guys remember this? So instead of parameterization, this is what I did. Oh, yeah, that one's negative. So now f of x and y, and if you remember, this gave me 1. No, this gave me -1, this one, and 3, and 3. If I plug it in, what is f of x and y? That original over there. I plug it, evaluate, this is max. So part of it was similar to the last time. Min. Are you guys ready to do one yourself? Okay. So that's exactly the last time. I just wrote it in different table. I didn't have enough space in here. I want to make sure it's fewer pages than last time, so I wrote it the other way around. Yeah, this one needs reading. Please write down whatever you get. Please write it down because there is a series of 3 iClicker questions. You completely solve that problem. Step by step through iClicker. Write it down. You need the formulas. Yeah, get the paper out. How's it going? Honestly, you need a paper. It's rough because you have to remember the formulas, then solve it. If you don't have a paper out, get a paper out. Or whatever you have. Yeah, you have something. You're ready. This one, just write down a short note what you're doing. Write down. What I want you to write down right now is what is objective function, what is the constraint, then pick one of the shapes for the constraint. Constraint comes with a shape. Curve of the constraint, right?
So the pictures don't line up.
Huh? The A is down there. So A and then B. So you have to figure out which one's the objective function. And then they line up. They line up.
Well, I'm confused. Over there is f(x), y.
No. That's the object. Okay, so there are 2 pieces. Find the objective function, only formula is given. Find the constraints, picture is given. So each A and B, which one's objective, which one's constraint? So f is the objective function. You're optimizing what? Objective function. Then the other one. Questions? Everybody okay? Ask louder. The objective function is the function you're maximizing. Objective is to maximize objective function. And sometimes I forget and I say goal function. That's the goal. But there's a constraint to it. Which one's the constraint now? Everyone okay, Duncan?
Define the maximum. Oh, I mean, that's pretty simple.
It's pretty simple, but it takes a while. So write it down, please. Hold on. What is that? What are you trying to maximize? X times y? You're trying to maximize x times y. That's objective. You're trying to maximize what? It says maximum product of two positive numbers. So x times y is the maximum. That's objective. Pictures are for the constraints. Constraint. Do you see constraint is this? Objective is that. So they're two different things. Okay. So what is the answer, my friends? 4, 3, 2, 1, 0. Okay, so you guessed it. Now I'm asking you to find gradient of f equal to lambda gradient of g and g of x and y equal to constant as three different equations. Three equations. Write them down. The constraint is a little finicky. You saw the constraint wasn't closed. I'm going to go back to it. Sure. Let me get my thing to point. Oh my, I still have two examples covered. Gosh. So how's this going? Gradient of f. What is g? G of x and y. What is that? Why? Somebody say louder. G of x and y is equal to x plus 2y? X plus 2y? G of x and y is x plus 2y. Okay, I'm giving you one little piece. Which one is constrained between C and D? Constraint equation. C. Remember, D is just reiterating the objective. D is reiterating the objective. Is D supposed to be in there? No. D is not part of the three equations. Two equations of the gradients parallel to each other. Gradients parallel to each other, and then one constraint. Are we getting there? Can you guys all write those equations that are good down? Write them down because I'm asking you next step to solve it. Start solving that because I'm asking you to do that. Next step. Did you write it down? Start writing this down. What is the first equation that is true? Gradient of g is 1 and 2. And then, say again? Okay. So, 4, 3, 2, 1, 0. What is the answer? C cannot be the answer. C is the curve of the constraint. Remember, constraint has to be in the equations. Constraint has to be in the equation. Look at this. Constraint has to be part of the three equations. C cannot be it. What? 4, 3, 2, 1, 0. You can change your answer if I'm telling you the answer. Go for it. So the equations are y equal to lambda, x equal to 2 lambda, x plus 2y equal to 12. And what is it asking, maximum or minimum? Max. So find x, find y, find the maximum. Find x, find y, find the maximum. Eliminate lambda. How can you eliminate lambda? Giving you a minute to do it. What did you get? No, do this, do this. No.
So how do we know if it's the max?
Okay. You found one. Put that in, and then I'll talk to you about it. Doing okay? Yes.
I'm just trying to figure out why I'm confused in my thinking. Plug in y equals lambda. Plug in y for lambda. Get x equals 2y. Plug in y here.
Y is going to be what? Which is 4y equals 12? That's just y. So what was x? 2y, right? So x is 2 times 3, 6. And then what you're trying to find maximum of. What is x if you solve? What do you get for x? The 6. What do you get for y? 3. What do you get for x times y?
18.
What do you get for x? What do you get for y? See? No, the other way. 6 and then 3. I'm going to talk about that. Somebody already asked the question. Thank you for asking it. I wanted the question to come up. 4, 3, 2, 1, 0. So what is the question, my friends? The question is, how come only 1 point? Because constraint was kind of construed. Let's go back to the shape of the constraint. It was not closed. And curve of the constraint wasn't just that equation. There was x bigger than 0 and y bigger than 0. So there's multiple things going on in there. So you have to do a little bit of this, a little bit of that. So what happens, this wasn't closed, but it was bounded. If I include the endpoints, what is x times y at the endpoints? Do you see the yellow points? What is the x of this yellow point? 0, x times y? 0. What is the y of that point? 0. What is x times y? 0. So you really, the three equation inequalities that you had made the constraint. And the 2 endpoints, if I include the 2 endpoints, I would get zeros. Right? So there are always, if it's not closed and bounded, there are methods to still find the local extrema. What's that? No, not today, I'm sorry. So that was the story. Any questions on this? That I actually had other points in there, it was just because I wasn't completely doing the... Okay, Now, what is this question asking? What is it that I'm trying to optimize? What does closest mean? Think English, not math. Near something. How do I measure nearness? Distance. So what are you trying to optimize? The distance. So I'm trying to really optimize this from origin. This is the distance from origin, right? Do I like square root? No. If I optimize this or optimize this, do I get the same values? No, I mean, you get the same points that makes this and that optimized, right? Because, yeah, there is a little bit of a story in there. There is a one-to-one function. The square root is a one-to-one function and does that. But whenever I optimize this, those points would work here. Fair game? Yeah. So I'm going to optimize this instead. Goal is this, but I don't like square root, so I go and I choose this. Because I know if this is optimized, then square root of it is optimized. Now, so this is the objective. And tell me the equation of the other one. Y squared, z squared equal to 1. Okay. Now how do I do it? Again, it's like 2-dimension, except that you have 3-dimension. So I find gradient of f, and that is 2x, 2y, 2z. Gradient of g is what? 2x, y squared, z squared, 2y, x squared, z squared, 2z, x squared, y squared. Setting this equal to lambda gradient of g gives me 3 of them. Gives me 2x is equal to lambda, 2x, y squared, z squared, 2y gives me lambda, 2y, x squared, y squared. You guys are enjoying this? No? Okay. So 3 equations. What else do I have? The constraint. All good? So what do you guys suggest to do first? Get rid of the lambda. Solve for lambda. Oh, before I do that, I'm going to get rid of this. Oh, what do I need to do, though? If I get rid of this, I have to imagine x equal to 0 could be an answer. But is that even possible? No, why is it not possible? 0 cannot be, not possible. The same for y is not 0 and z is not 0. So I can actually get rid of them without worrying that they are a solution. Sometimes they are. This time, I will make sure that sometimes x equal to 0, y equal to 0 is a solution. So be careful. Consider it. Make sure that it's actually not a solution. Otherwise, count it as solution. Here, from here, I get y squared, z squared equal to 1 over lambda. Agreed? X squared, y squared is equal to 1 over lambda. No. Why did you guys not yell at me? Thank you. Thank you for being polite. This was wrong. Fix it. Now I can set them all equal to each other. I get y squared z squared equal to x squared z squared equal to x squared y squared. If I look at these two, what do I get? So it's x squared is equal to y squared. What about these two? Z squared is equal to y squared. So all of the squared ones are equal to each other. Fair game so far? Blue. Now the last step is to plug them all in. So instead of y squared, I plug in z squared. Instead of z squared, I plug in y squared in the constraint. So constraint, x squared equal to 1. What do you get? No, x to power 6. That's okay. X is equal to plus minus 1. Same thing for y, right? Same thing for z. I'm writing it up because you will get it soon enough, but the first time I won't write all of them up. Fair game? So how many points do I have? 8? 2 times 2 times 2, 8 points. Plus minus 1, plus minus 1, plus minus 1. One more. Possible. No color streamer. So now I want to tell you, if you plug this back to square root of x squared plus y squared plus z squared, all of them, 8 points, all of them are going to be square root of 3. Now, I want you to think about this. There is a surface. The surface doesn't go through origin. And I found a critical point that gives me square root of 3. Can this be maximum or can this be minimum? It has to be minimum, right? We know that if there's a surface in there, there's a minimum distance from geometry. And that's how I know it's minimum. Why is this not giving me a maximum? That is not bounded. Constraint is not bounded. Can I show you a cool picture? This is the graph of the thing. Huh? Yes. That's the graph. I made it 2 different shapes. That's the graph of the constraint. Can you see the red points? Can you see there are 8 of them? Those are the closest points to origin. And sometimes you have to solve for this. God dang it, I didn't finish this section. I'm in a lot of trouble. Okay. Can I say something in 30 seconds? I have to put it in the lab. I can't finish it on Monday. I put it in lab. Sometimes things in lab are new, right? That's okay. Hello. Oh, go out that door. The door right on your right. Right after you get out, knock on it and then ask. Take care. Hello.
Are you doing the next class or?
I'm doing next class.
Okay, perfect. You don't need anything?
No, I'm good.
Okay, great. We'll be in the back if you need it.
I love the necklace.
Oh, thank you. My mother made it.
I brought this. I didn't do it with them. You're welcome. Oh, this was supposed to be something cool too. Look at this. So when we're doing the curve of the constraint, right, like that, and then you can see that when you get to a level curve that is maximum, it's going to be It's like that's the level, that's the curve of constraints, that's the value, curve of constraint f of the curve of the